previous video we have seen a closed set and some examples, and we have proved this theorem. Now let's go for the next theorem. Okay, in the previous video we have seen this closed set and all these examples, and we also saw this theorem and proof. So let's go for the next theorem. The theorem. So theorem statement is Y be a subspace of X, then the set A is closed in Y. So we have this Y which is a subset of subspace of X. So you have X and in this you have this subspace Y. Okay, this was given and you have to say some set A is closed in Y. Something inside this Y, we have to say that A is inside Y, and we have to say that A to be closed in Y, that if and only if. So you have to say this A is closed in Y only when it equals the intersection of closed set of X with Y. So this A should be equal to the intersection of closed set of X. So this C is the closed set of X. This C is something which is closed in X. So this one C intersection with Y, if it equals the A, then A is the closed in Y, and conversely it is true because it is an if and only if statement. So this A is equal to intersection of C and Y. If it is so, then I can say that A is closed in Y, and if A is closed in Y, then A equals the intersection of some closed set C and Y. So this is what we have to prove, and for this we need these two diagrams for proving. Okay, I have this topological space X in which I have this is my Y and this is my C. C is nothing but I am naming it as C, which is a closed set of this X. Intersecting point, intersecting region is my A. Okay, so I have A is equal to, I am calling A is equal to C intersection Y. So I am assuming this and I have to prove this A is closed in Y. So where C is nothing but I am naming it as C. So I have to say this C is the closed in X. So I just named it as, because you have this much of statement, the intersection of closed set of X. So the closed set of X I am naming it as C. And C intersection Y is equal to A. So I have taken this and I am going to prove this is A is closed in Y. And we should know that if A is closed in Y, then we have to say that A is closed in Y. This implies Y minus A is open in Y. This is the result we can write in this way. So when you have to say something is closed, you have to say that complement is open. So that's a result. So that's what we are going to take and prove. So you have taken A equal to C intersection Y and you have named this C is a closed in X. So the next foremost step is you have to say X minus C is open in X, because this is closed and X minus C is nothing but C complement. This is closed means its complement is open. So after this step you have to write this one. Okay, from this step they have gone to X minus C intersection with Y is open, but you should know how it is open, right? Open in Y. So we have got this one and they have gone to this step, but how is this possible? So for this you should know the subspace topology definition, and subspace topology is denoted by tau Y, where Y is the subspace of X. Okay, for this, for the subspace topology is defined as U intersection with Y, collecting U intersection Y, where this U belongs to tau. Tau in the sense, specifically I can say it is the parent space topology. So the subspace topology, the collection of topology on X is tau X, and U belongs to tau X means U is open in X. So I am collecting U which is open in X and I am intersecting with the Y. So from this diagram you can understand I have its, okay. So I have topology on its also. So that is the collection of all open set inside this its, that is U. So when I'm taking one U and I'm intersecting with Y, so that I'm getting one of the element. Then taking another element in the sense it will be a open. So another open set intersecting with Y. So I'm going to keep on doing this to collect the tau Y. If I complete this, then that collection becomes the tau Y. So here I got x minus e is open in its. So you can compare with this where U is open in tau its. So this is nothing but x minus e belongs to tau its, because open in the sense that belongs to this collection tau its. So x minus e is open. So x minus e will be coming here, intersection with Y, because it is my subspace. So when I'm intersecting, this becomes open in Y, because that becomes an element of tau Y. When you know, you should know that when element belongs to the topology, that element is becoming a open. So whatever the element which comes inside the topology, it is open. So I'm getting x minus e intersection with Y is open in Y. See, for next step, if you want to move for the next step, these are all the just result, okay. You don't want to write in between, but you should know the subspace definition, subspace topology definition. So this is the result and this is also the result, okay. So when you want to move for the next step, but in order to move, you need A is closed in Y. That is what you have to prove, right? So this actually it comes from Y minus A is open in Y, right? Y minus A is open in Y. So from this I can get A is closed in Y. So I'm just going in the backward, okay. So you need this Y minus A. You got this is open in Y. So just connect this and this. I mean whether you are getting this is equal to this. So for this we need this diagram. With the help of diagram you can understand it easily. So x minus c, just think what will come, that is complement. This area will comes intersection with Y. So what comes is this part, okay. So I just shade it over. So this part will come and you can observe that it is actually Y minus A. Y minus A. So this can be replaced with this. I can say that x minus C intersection Y is nothing but Y minus A. And you know x minus C intersection Y is open in Y. So Y minus A is also open in Y. And hence I got A is closed in Y. So first part of the proof is over. Now conversely I assume that, so for the converse part, you need to assume this A is closed. A is closed in Y. So I have assumed this A is closed in Y and I have to prove A is equal to C intersection Y, where C is closed in X. So what? This is nothing but whatever the set which is closed in this Y subset of X. Y is nothing but a subset of X, right? So whatever the thing which you have to say it is closed, it is actually nothing but a intersection of that Y with some closed set in X. For the converse part, consider this figure and we have to assume this A is closed in Y, and we have to say that when it is closed, then it is intersection of, it is of the form of some intersection C with Y. So whenever A is closed, it is of the form C intersection Y, where we know that C is closed in X. So this is what we have to prove. Since we are given with this A is closed in Y, we can say that A is closed in Y. So Y minus A you have to take. Y minus A is open, because it is assumption, and from this step you can directly say that Y minus A is open. So when it is open, and you have to say it is open in Y, because it is closed in Y, so a complement will be open in Y only, not in X. So we should not confuse over there. By definition, it equals the intersection of open set U of X with Y. So since it is open in Y, it means y minus a is in some tau y. That is topology with respect to it is a subspace topology. So y minus a is in tau y. So it is of the form some u intersection with this y, because you already saw the subspace topology definition. So y minus a belongs to tau y means, because it is open in y, right? So y minus a belongs to tau y. It implies it is of the form u intersection y for some u, okay, where u belongs to tau. So you know that, okay? So this is of the form u intersection with y. So you have to write where u is open in H. You can write y minus a is equal to u intersection y, where u is some open in H. So when you have got this statement, you can write h minus u. H minus u is closed in H, because from here you can write this complement is closed in H, because it is open in H, its complement will be closed in H only. So I have got up to this. Now let's draw the diagram. So I have got this H, whole set H. I have some y inside H, which is a proper subspace of H, okay? Now I have y is a is closed, because we have my assumption is a is closed, so I'm just taking some closed inside this y. So I have a which is closed in y, which is my assumption, a is closed in y. I have to prove this a is equal to some intersection of y with some c. I'm gonna say that this c, some c, right, some closed c. So this is closed, x minus u is closed. So I'm just going to say a is equal to x minus u intersection y. So that is my claim actually. A is equal to x minus u intersection y. This is what I have to prove, because I have to say a is some intersection of with y with some closed set of x. That is what the statement is. So if I say this, then my theorem gets over. So a should be equal to x minus u, where u is open in H. So this is my u, and if I remove that u, I'll get this part, this whole part. When I intersect with it, I'll get this a. Okay, so my a becomes x minus u intersection with y. Hence my theorem gets over. Next theorem, y be a subspace of X. Just consider with the figure. If a is closed in y and y is closed in H, so a should be closed in y and y should be closed in H, then only we can say a is closed in H. Okay, closure and interior of a set. So the definition goes like this: a topological space H, so the interior of a is where a is a subset of H, so it's defined as the union of all open sets contained in a, whereas the closure of a is defined as the intersection of all closed sets containing a. Containing a, it's contained in a. So there is a difference, and these two things definition is quite important for problem solving. So we know this result: interior of a which is contained in a, which is contained in a closure. So this is a quite trivial thing. Now let's go for the theorem. Y be a subspace of X. So already we know this. A be a subset of Y. So there is something A which is in Y. A closure. Okay, where they are saying this notation is for closure of A in X, not in Y. So this is the closure of A in X. Okay. So now if these are all holes, then the closure of A in Y. So I have a closure in X. But how the closure of A in Y looks like is actually equals to A closure intersection with Y. So this theorem is like quite familiar, like looks similar to the 17.2 theorem, right? So let's prove this theorem. I'll just give a brief explanation on this theorem quickly. Okay, so we have Y is a subspace of X and A be a subset of Y, and A closure denotes the closure of A in X, not in Y. Okay, but if you want to know the closure of A in Y, which is not actually a closure. It will be intersection with y. So it looks like a similar to subspace topology definition. So a closure will be in y will be a closure intersection with y. Okay. Now you have to name this thing closure of a in y as b, because we need some smaller notation. So just for that I have b. So we have to say b is equal to a closure intersection y, and we are given with a closure. So a closure implies closed. So that is the first point we should know. Obviously whenever we are going to use closure, you can say that is also a closed. So a closure is closed in its. From this we can say that a closure intersection y is closed in y. This is by the subspace topology definition. Okay. So a closure is closed in X from the given statement, and from this immediately it is arriving that a closure intersection y is closed in y, because everything we need in y. Okay. So I have got this one, which is like got this one in the sense I have got this as a closed in y. Now by theorem, the theorem statement is like a is closed in a y if and only if a can be written as some closed element of its intersection with y. So if I can write like this, it is closed in y, it is an if and only if statement. So a closure is closed in its, a closure intersection y is closed in y. So these things I have got very easily, I have got. And I have to know, I know that a closure intersection y obviously contains a. Why? Because the closure definition goes like this: intersection of all closed sets containing a. That means this closure will contain a obviously, because that is the way it formed. Okay. So a closure will contain a, y also contains a. So on the whole, a will be contained in a closure intersection y. So this is the one part. Now I have this b, because I have done all the experiment with this RHS, so I have to come for the LHS. So I have b, which is nothing but closure of a in y. That definition should be little modified for this, because it is closure for x, but it is closure of y. So it is an intersection of all closed subset of y containing a. So this is the, by definition I can write this b, and this implies b is a subset of a closure intersection y, because it containing a matlab like a is a subset of a closure intersection y. From the definition, these two implies this thing. Okay. So b is a subset of a closure intersection y, and I have to prove conversely. I mean conversely in the sense a closure intersection y contained in b. So in the way I have to say, for that I know this is closure. So obviously what you can say, it is closed. So b is closed in y. When it is closed, see this is going in this way only. When it is closed, okay, we have to say this as by the theorem. By the previous theorem, you can say related with the y by intersecting. So b can be written as u intersection y, where u is closed in its. So this is by the theorem which we have proved also. So b is equal to u intersection y. Why we need this? Because you have this u, but you have to replace it with a closure. So what is the relation between u and a closure? So u is closed in its. Instead of writing in that way, u is closed in its containing a. So that word is important, because u will also contain a. So u will be containing this a. So a closure is contained in u. So taking intersection on y on both sides, we get this one. So if we get this relation, and you know this u intersection y is b, so I can replace this with b. So a closure intersection y is contained in b. So I have already got this, and I have got this now. So by equating I am getting this. So hence the theorem proved.